Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we were talking about the measurement of strain, and we just talked about, or we were discussing about the construction of 45 Mohr cycle for the 45° strain rosette. Okay. So, I mean if you come back to this figure again, so basically we have got this construction of the Mohr cycle by following the 45° strain rosette. Okay. And we have got 3 points, point A, C and B. So, these 3 points basically are giving me the normal strain measurements, okay, for 45° strain rosette. Okay. So, that those normal strains are coming from the strain gauge reading. Okay. So, now once you construct this Mohr circle, basically you will be getting the information about other strain components, epsilon x, epsilon y, gamma x, y, or any arbitrary coordinate system. The strain components are obtained from this Mohr cycle. But in the last lecture we were talking about whether this construction, whatever construction is done, so that is correct or not, and I said this is incorrect construction. Now, why it is incorrect? Let's discuss that thing about. Okay. So, now if you see, okay, your 45° strain rosette, so the orientation of your 45° strain rosette is, this is your A axis and this was B and this was C, right. Okay. So, now in this coordinate system, if you go or if you rotate 45° in the anticlockwise direction, you should get B axis. From A axis, if you rotate 45° in the anticlockwise direction, then you should get B axis. Similarly, from A or B, whatever, if you rotate another 45°, then you will be getting C axis. Now, you need to see or need to check that whether you are getting the same sense of rotation in the Mohr cycle or not. Now, let us see here. Now, from A, if we go to B in the Mohr cycle, you need to go up to 90°, right, 90° anticlockwise. But here in this construction, you have to come 90° in the clockwise direction. Similarly, from B to C, if you want to find out, so that angle is again 90° in the clockwise direction. So, magnitude wise it is fine, but the thing is that the sense of rotation is completely reverse than the actual coordinate orientation, right. Actual coordinate orientation says the angle between B and, I mean angle between B and A is of course 45°, that is okay, but from A if you go the 45° rotation in the anticlockwise direction, then you should get B. Similarly, from B if you go 45° anticlockwise rotation, you will get C, but in the Mohr cycle you are just getting reverse. So, therefore, this construction is incorrect. Now, what should be the correct construction? Let us talk about that thing here. So, this is my correct construction. Now, when we laid off, okay, point A or point C, okay, we laid off point A in above the epsilon axis and point C below the epsilon axis, right. But nobody told me that why point A will be should be laid off in the above of epsilon axis. Who told me? Nobody told me. I just took it arbitrarily, right. So, I laid off AA which is equal to dB, that is fine, but I chopped the point A on that vertical in above the epsilon axis, but that may not be true. So, what we are doing here, we are laying off AA in such a way A point is coming below the epsilon axis. Similarly, the C point is going above the epsilon axis. Now, you construct the Mohr cycle by following the same process whatever we have discussed in the last lecture. So, if you construct the Mohr cycle, now you see from A you are getting 90 degree to reach B in the anticlockwise direction, and from B if you want to reach C you have to go to 90 degree rotation again anticlockwise direction, and which is matching with this. Okay. So, therefore, this is your correct construction. Okay. So, this is all about your strain measurement and strain rosette, that is the arrangement, and which is very important if you are going to do some experiment and if you want to measure some strain, and then from there if you want to get the value of stress and other things, other information, then this discussion will be very required. Okay. So, this concept will be very essential. So, with this basically your concept of stress and strain chapter is over. So, now we will take couple of numerical examples to understand this whatever we have discussed in this particular chapter. Okay. So, let us talk about that. So, here is your first numerical problem. Let me write down. We consider a thin sheet pulled in its own plane, so that the stress components with respect to the xy axis are as given in figure. Okay. So, figure I will be showing later on. Determine the stress components with respect to AB axis, which are inclined at 45 degree to the xy axis, and also find out locate the principal axis and evaluate principal stresses and locate the axis of maximum shear and evaluate the corresponding stress components. So, the figure is like this. 110 meganewton per meter square, and this is your x axis, this is your y axis. Your shear stress is 40 meganewton per meter square, and tau xy is equal to tau yx. So therefore, I am not showing all, I mean everywhere 40 meganewton per meter square, that is quite understood, and sigma y is meganewton 50 meganewton per meter square, and you have the axis AB like this, which is making an angle 45 degree with x axis. Okay. So, therefore, the problem says that we consider a thin sheet pulled in its own plane, so that the stress components with respect to the xy axis are as given in figure. Okay. Determine the stress components with respect to AB axis, that is your some arbitrary set of axis, okay, which are inclined at 45 degree to the xy axis. Locate the principal axis and evaluate principal stresses, and locate the axis of maximum shear and evaluate the corresponding stress components. So, now this problem can be solved by using the equations whatever we have derived, but however, to understand the Mohr cycle in a better way, we are going to solve this problem using Mohr cycle construction. Okay. So, let us do that. So, let us construct the Mohr cycle first. So, this is your sigma tau space, this is the Mohr cycle of stress we are going to draw. Now, what are the things I know? I know sigma x equal to 110 meganewton per meter square, sigma y equal to 50 meganewton per meter square, and tau xy is positive or negative? That will be positive, because on positive plane along positive direction the shear stress is shown. So, that is also positive 40 meganewton per meter square. So, all stress components are positive, sigma x, sigma y and tau xy all are positive. Okay. So, therefore, the Mohr cycle, let me draw it. So, this is your Mohr cycle. Okay. This is the center of the Mohr cycle, and these are 2 points. Basically, these points you have to locate first. I have drawn the Mohr cycle first, that does not mean that you will be getting the Mohr cycle first. First you will locate, as per our construction procedure, first you locate point x, point y as per that combination. So, point x coordinate is 110 40 and point y coordinate is 50 40. Okay. Now, you may ask me why I have shown x point below the sigma axis, and that is known to you, because we are following the sign convention, where if you have positive shear stress, okay, then it will be the x will be plotted below the sigma axis. Okay. So, here your shear stress is positive. So, therefore, x is coming below the sigma axis. Okay. So, now from this we can calculate C. C is nothing but the distance, this is your distance of the center of the Mohr cycle from the tau axis. So, C can be obtained as sigma x plus sigma y by 2, right. This is your sigma x 110, this is your sigma y. So, this will be coming at the midway. So, sigma x plus sigma y by 2, and that comes as 80 meganewton per meter square. Okay. Similarly, the radius of the Mohr circle, that you know already, we have put the expression sigma x minus sigma y by 2 whole square plus tau x y square to the power half. If you put, you will be getting the value 50 meganewton per meter square. Okay. So, these are the values will be required, I mean these are the parameters will be required later on for calculation of remaining stress components. Well, so now your AB, if you look at, this is your physical plane, this is your stress plane as per our definition. So, in the physical plane, the angle between x axis and a axis is 45 degree in the anticlockwise rotation sense. Okay. Therefore, I can locate here the angle, the axis, the plane, basically a plane and b plane like this. So, from x point I have to rotate 90 degree, okay, in the anticlockwise direction to get plane A. So, that is nothing but so this is your A and this is your B, and this angle is 90 degree. Okay. Same sense of rotation, from the physical plane we are coming to the stress plane, only twice, right. That was 45 degree, now it will be coming as 90 degree. Now, if I define this angle as twice of theta 1, then I can calculate that angle as sine twice of theta 1 is equal to tau xy, you can see tau xy by r. So, this is your tau xy and this is your r. Okay. So, sine twice theta 1 is equal to tau xy by r. From this I can get twice theta 1 is equal to, by putting the values, numerical values, I will be getting that equal to 53.13 degree. Okay. Now, angle AC1, what is 1? This point is 1, okay, and this point is say 2. So, angle AC1 is therefore your 90 degree minus twice theta 1, which gives me 36.87 degree, which is equal to BC2, which is equal to, obviously, which is equal to BC2, this angle. Okay. So, from this I can get the stress components in AB coordinate system, that means the arbitrary set of coordinate system. Sigma A is nothing but C plus R cos 36.87 degree. Just look at the figure, sigma A, that is a C plus this much, okay, from C to this point, that will be obtained as R cos 36.87 degree. So, if you put the values, it will be coming 120 meganewton per meter square. Similarly, sigma B I can get C, what is sigma B? Sigma B is here, right. So, this is your sigma B. So, sigma B is nothing but C minus R cos 36.87 degree, that comes as 40 meganewton per meter square. Now, what about tau AB? Now, tau AB is nothing but, this is your tau AB, this is your tau AB, or this is your tau AB, whatever you say, this is your tau AB. Okay. So, tau AB is R sine 36.87 degree. Now, what is the sine? So, sigma A is positive, fine, because that is in the positive sigma direction. Sigma B is also positive. Now, what about tau AB? Is it positive or negative? You just look at this x point is getting mapped to A point. That means, if A point is coming above sigma axis, then that shear stress is negative as per our sign convention, because x is getting mapped to A or x is getting rotated to point A. So, A is lying now above sigma axis. Okay? So, instead of A you can consider x prime. So, x is mapped to x prime and x prime is lying above the sigma axis. So, therefore, your tau AB must be negative as per our sign convention. So, that is coming 30 meganewton per meter square. Okay. Now, you quickly we can say sigma 1, that is principal stress and principal stress axis, and maximum shear stress and maximum shear stress axis. Okay. So, these two things we are going to find out. So, sigma 1 by definition, sigma 1 means this one is sigma 1, right. This is your sigma 1 by definition C plus R. So, that will be coming as 130 meganewton per meter square, and sigma 2 is C minus R. This is your sigma 2. So, that is coming as 30 meganewton per meter square, and I know this twice theta 1 is known to me, right. Twice theta, what is twice theta 1? This angle is nothing but the angle made between x axis and major principal stress axis, that means axis 1. So, in the stress plane this is twice theta 1. So, in the physical plane it will be theta 1. So, theta 1 value is nothing but your half of 53.13 is nothing but 26.56 degree. So, therefore, your, so this is your x and y axis, and this is your 1 and 2 axis, which is making an angle in the anti-clockwise sense of rotation 26.56 degree. Okay. So, this is done principal stresses and orientation of principal axis. Okay. Now, coming to the sigma d, this point is a d, this point is E. So, sigma d is nothing but equal to sigma E is equal to C, right. So, that is 80 meganewton per meter square, that is the normal stress on the plane on which maximum shear stress is acting, that will be same. And twice theta 2, if we consider this angle as theta 2, twice theta 2, that means the angle between the major principal stress axis and the axis on which the maximum shear stress is acting, that is nothing but your 90 degree. So, twice theta 2 is equal to 90 degrees, therefore, theta 2 equal to 45 degree, right. So, therefore, if this is your xy plane, so from one axis it will be further 45 degree, right. So, this angle is your D and E, and this angle is your theta 1 plus theta 2, that is nothing but 71.56 degree. Okay. So, you have got and of course, the maximum shear stress, that is also important to be determined, that is nothing but the radius of the Mohr circle, and that is 50 meganewton per meter square. So, you have got maximum shear stress, you have got major principal stress, minor principal stress, and the orientation of the principal axis and orientation of the axis where maximum shear stress is occurring. So, I will stop here today. So, I will take one more numerical example in the next class, and then we will try to establish the relation between stress and strain. Okay? So, thank you very much.